Okay, well, thank you for the introduction. It's fantastic to be here. I'm going to be closer to the microphone so that everyone can hear me, and I'm very impressed by all of you who are here so early this morning after a very late night on that boat. Oh, let me turn my slides back on. Okay, so today, I wanted, oh, no. Slowly, yeah, but it's also the wrong size, so we're going to fix that. Great. Now it's the right size. Okay, so today I want to tell you about some techniques that I've used in automated machine learning that I think are a little bit less common. I'll show you some applications where I've used them, but I also want to convey to you a little bit of my research story through automated machine learning, and give you a little sense of sort of the flow, right? How do I choose projects? What works out? What hasn't worked out? I started working, so my background is not I guess, you know, no one's, if you're old enough, no one's background is in automated machine learning because it's a relatively new field. So I first heard about automated machine learning in 2017. My background is in large-scale convex optimization, so constrained optimization, gradient-based optimization. And I do a lot of looking at the structure of data sets and trying to understand how the structure of data sets can speed up optimization algorithms or make them more efficient, memory efficient, compute efficient, things like this. And I got involved in AUTOML through a DARPA program, D3M, Data-Driven Discovery of Models, which really catalyzed a lot of automated machine learning in the United States. So I got pulled into this mostly because of my work on imputing missing values, which, you know, again, you know, you sort of see the research arc when you get a couple of years out. I worked a lot on imputing missing values, and now, I think you heard in the AutoGluon presentation, they don't recommend imputing missing values, and I also do not recommend imputing missing values. And missing values are usually informative, interesting. If you impute them, you might lose that signal, and that's a bad thing. Okay, so we have actually have a paper on that in KDD of this year. Okay, but at the time, we thought imputing missing values was a good idea. And I was at you know, this sort of initial kickoff for the D3M program, which ultimately led to Alpha D3M, which you saw presented at this conference many, many years later. And I remember having a conversation about, you know, imputing missing values with some people at the conference, and they said, well, you know, what about automated machine learning? Like, is that a missing value problem? And I thought about it. I was like, that's kind of interesting. In some sense, it is a missing value problem. Okay? And that catalyzed the approaches that I'm going to show you today. Okay, so let's get into it. So, why automated machine learning? I don't have to make the case to this audience that the best machine learning model obviously depends on the data set. Okay, so different machine learning models perform best on different data sets. How do we choose the right one? So we're going to start in this setting where we're choosing, let's say, a pipeline of machine learning components. Okay, and this was the original vision of the D3M competition. It's the sort of the cache setting of combined algorithm and hyperparameter search. Okay, so given a raw data set, you're going to make a bunch of choices, right? First, you've got to handle your missing values. Maybe you'll impute them by the mean. Maybe you'll impute them by something else. Maybe you'll add a missing indicator. I'm using the missing indicator method as, I guess, the sort of more modern recommendation. Then you got to encode your categoricals if you're going to use a model that can't handle them natively. You might need to standardize your data. You might reduce the dimensionality or select features. And then you might choose an estimator, maybe k-nearest neighbors, maybe XGBoost, maybe CatBoost, maybe a deep neural net, something, okay? So that's a lot of choices. How are we going to make all these choices? Well, not by doing it by hand, okay? Not by trying all the models. We're going to do it with automated machine learning. Okay. Why is this worth doing? Why is this worth doing? Why not just use the same algorithm for everything? We're going to return to this question later, but for right now, you know, here's a motivation for doing automated machine learning in the first place, right? Which is that if you actually exhaustively compute these things and you try all of these methods, right, every combination on all of the data sets from on 215 medium-sized data sets from OpenML, okay, you find that, okay, gradient boosting is a really good idea. But it's only the best 38% of the time. It's not the best all the time, right? Other things are also have a substantial fraction of the weight, right? So the next step is multi-layer perceptron, deep learning, whatever your favorite deep learning method is, k-nearest neighbors, blah, 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 okay? And I should point out this and many other, actually the bulk of the work that I'm going to talk about here was led by my PhD student Chengrun Yang, who's now at Google DeepMind, okay? So whenever you see Yang, it's Chengrun Yang, okay, who's at Google DeepMind. So you can look him up and find, follow the rest of his awesome work. Okay. So how do we choose the best machine learning model for a data set, right? And not just the estimator, by the way, right? The entire pipeline, that's a lot of components. Okay. No free lunch, there's no one model that works best for every problem. Okay, there's actually a theorem supporting this. Okay, so what kinds of AutoML are there? What kinds are we concentrating on today? So there's hyperparameter tuning, which I have heard at this conference frequently called optimization. People say optimization, and they mean black box optimization, no gradients, in usually a low-dimensional space, okay? Which as a high-dimensional constrained optimizer with gradients, I kind of object to, but okay, we'll go. So I do feel the need to clarify, okay? So hyperparameter tuning. Okay, there's combined algorithm and hyperparameter search, which is the setting that we'll be working in mostly in this talk. Neural architecture search, meta learning, right, which is learning to learn, which is generalizing from a corpus of tasks to a new task. Okay, so we're going to be in, and of course, different kinds of data sets demand different kinds of methods. Okay, but I'm going to talk about meta learning for combined algorithm and hyperparameter search, cache, on tabular data. Okay. Why do I make these choices? Actually, the techniques are pretty general. I mean, I guess the techniques are all using meta learning. Meta learning is essential. Okay, but why cache on tabular data? Do you have an idea? Why did I study cache on tabular data and not like neural architecture search? Why would I have done that? Fast, excellent. I can afford it. Yes, yes. Excellent. Okay. So I don't think that there's anything fundamental about the sort of these techniques and these problems, but you can do the demonstration. Great. Okay. So how does meta learning work? Because actually we haven't seen that much on meta learning in this conference so far. So here's the idea, right? Learning, right? What do? You take your data set and you split it up into the training set, the validation set, and the test set. Yeah. Train on the training set, check, maybe choose hyperparameters on the validation set, and see how it works on the test set. Great. Meta learning, what do? You take a set of data sets, right? You split up your set of data sets. You take some of the data sets, those are your training set of data sets. Some of them are validation data sets, some of them are your test data sets, yeah? So your meta learning algorithm, right? Well, maybe it has some parameters, your meta learning algorithm, okay? And you train those parameters, those meta parameters, on your meta training set. Okay, maybe this is just words at this point, okay? But the point is that you need to do proper cross-validation of your meta learning algorithm, okay? It's actually very easy to get your meta learning algorithm to overfit to your set of data sets, if you're not careful. Okay, and what's the joy of meta learning? The joy of meta learning is that unlike many of the very expensive approaches that you've seen sort of earlier in this conference, using like evolutionary search to do, to find better optimizers, here we can pick a new model, a model on a new data set without any expensive function evaluations, right? So rather than, finding a new optimizer by, operating, we're finding a really good optimizer for CFAR by operating on CFAR, what did we hear, 10,000 CPU times 5 days, right? The idea is that we would be able to pick a good, let's say, optimizer immediately, almost immediately. Okay. Great. So what kinds of machine learning models can we use when the samples are data sets? Okay. So I don't know if this is obvious to you now. When I first thought about this problem in 2017, this was very confusing to me, right? Because the data set, they're big and they're ragged. They're not the same dimensions all the time, right? So how do you take a data set and turn it into, features that you could plug into your machine learning model, which expects that, everything be the same dimensions? Okay? Now this had already been studied, so which was ways of featurizing a data set, turning it into a set of features that might be relevant, and then you can use traditional machine learning. As soon as you have features, right, then you're golden. You can use any machine learning algorithm you want. Okay, but this actually made me a little bit uncomfortable. Like, how do we know it's the right set of features? How do we know which features are right? Like, what if we're just missing something? What if there's something in the structure of these data sets or the relationship between learners and data sets that we don't even know how to quantify, right? Or what if it's expensive to quantify, right? What if it's as expensive? What if finding good features is as expensive as running the algorithms? Okay, so this is where a recommender systems approach, like the ones that I'm going to show you about, might come in, right? So we can discover the features that best predict performance of different learning algorithms on your data set. Okay. And then now, in the modern era, right, there's a really easy answer. You want to featurize whatever? Whatever. You can featurize whatever, right? Anything you can serialize into text, you can feed to a large language model, and then you can, if you have access to the weights, you can actually, look at the, an embedding, right? Or you can ask it to, give you a compressed representation or something of the data set. Okay. So now you've got a general purpose version. Now, is it any good? Does it actually do automated machine learning? These are questions that we have for, large language models, right? Okay, so I'm going to talk mostly about the recommender systems approach, and I'm also going to return to this large language models question because I think it's the current relevant and pretty exciting direction. Okay, so data set meta features. How do we learn from meta features? So here's a list of the meta features in an early version of AutoSK Learn from 2015. Lots of meta features. It's not, it's a lot of meta features. Actually, it can take a while to compute all these meta features, is what we found. Okay, so once you have meta features, what do you do? In the sort of earliest versions of AutoSK Learn, it was something like this. You take the data set meta features, right? You use those to embed the data sets in some space. For your training set of data sets, you exhaustively compute the best algorithm and hyperparameters. For a new data set, you look at which data sets are similar in this feature space, right? And start with those algorithms and hyperparameters and then tune with Bayesian optimization. Okay? So that's a sort of traditional approach. I'm telling you about that so I can contrast that with a recommender system approach. Okay? So let me show you about an early recommender system approach. This is OBO. Okay? And our thesis here was that rather than predefining what the meta features are, maybe you can learn from the task itself. Okay? So you can run experiments on maybe other data sets, and maybe especially using fast-to-train models, and then use the low-rank structure of the errors of data sets by models to meta-learn. Okay. And this is similar to work that was sort of concurrent that used Bayesian optimization by Nicolas Fusi. Okay, so here's the idea. Okay. This is the technique, so if you just get this, then you'll be able to use it in all of your other work, okay? So here's the idea. So given M training data sets, N machine learning models, okay? And here I'm thinking about gridding out hyperparameters, okay? Because actually this method works better if N is larger and if M is larger. It works better and better and better, okay? So you take your algorithm types and then you grid out all the hyperparameters. So using your logarithmic grid or linear grid or whatever you want, okay? The more the better, no problem, okay? You're gonna measure the error of every model on every data set, okay? So if M and N are sort of moderate, it's actually not too bad, and this is the training phase, so we're allowed to do a lot of work, okay? If you think it's bad, you can also sample these, especially if you sample uniformly at random, that's even better, and the method works almost the same. We're going to form this M by N data table. Okay? So that's the error of the, there we go. The error of the, the ijth entry is the error of the jth model on the ith data set. Okay? So these x's are errors, or maybe they're accuracies, right? I don't really care. Depends what I'm going for. Okay. Now that I have this, I'm going to do something crazy. This is the crazy step. I'm going to do PCA. Okay. So, and in general, right, if I had missing entries, then I could do, you know, matrix factorization with missing values. It's a more complicated optimization problem, but it's not fundamentally different. Okay, so I'm going to do PCA. And here's what I like about PCA, right, is I had this big data table, and with PCA, I turned this into this factorized form. So here's how I'm going to think about the factors I get out of principal components analysis. I'm going to have I'm working with this pointer. Okay, I'm going to have one row here, xi, for every data set, okay? And I get to control the dimension of that row by choosing the k in PCA, yeah? So I get to decide, am I going to represent my data set as a 2-dimensional vector, a 5-dimensional vector, a 50-dimensional vector? I get to decide that, okay? That's cool. Similarly, for each learner, I get a representation. It's also k-dimensional, right, of each learner. And, okay, same thing, I get to control the k. This is pretty cool because now what happens? New data set comes along. This is test time, okay? This is what I care about. And at test time, of course, I don't know how any of the models performs on my new data set. But if I look over here in the factorized space, how many parameters do I need to estimate in order to understand how all the models will perform on my new data set? K. Yeah, exactly. I only need to estimate k parameters, and I control k. Okay? So if I want to model quickly, right, what do? I just choose k to be small. And if I have a lot of time on my hands and I really want a good model, I choose k to be large. Okay? So I can get a good estimate. I mean, I could also sort of do this dynamically and just sort of increase k, increase k, increase k until I run out of time. That's fine. So here's the procedure. Well, okay, I still need to estimate these parameters. I need some data to estimate the parameters from. Okay, so what do? I'm going to choose a couple of models to run. Maybe I should choose models that run fast, right? Maybe I should choose models that are informative. How do I tell which models are informative? Okay, think about that. I'm going to return to it. Okay, so I'm going to choose the models to run on the data set. And now look at the structure of this problem. I need to find some vector, xm plus 1, so that when multiplied by y, it gives me, right, it matches the data I've observed. What kind of problem is that? Machine Learning 101 here. What kind of problem is that? It's early in the morning. It was a late night. What kind of problem do I have to solve to estimate this new parameter, xm plus 1? Do I need to minimize the energy of a deep neural network? No. What do I need to do? Linear regression, thank you. Yeah, linear regression, 2-dimensional, okay? No problem. Good. Okay, so given that's right, linear regression, I get xm plus 1, I multiply it by y, and I can use that to impute the entries I didn't see. Cool. So let's think about it this way. The rows of x are data set meta features. The columns of y are model meta features. And the xi, yj's are predicted model performance. Okay. So that's kind of cool, right? It's kind of simple. I mean, of course, you could complicate everything. You could put a deep neural net in between these and say, I've just got some function of the x's and the y's. I'm going to estimate the y's, blah, blah, blah. Okay. There's some nice things about doing it with PCA, but let's check, does it make any sense to do it with PCA? Is this like a really bad idea because the data set looks nothing like a low-rank matrix? No, it's kind of decent. It's okay. It could be worse, okay? So here's the situation, right? We look at the data set, we look at that data table, that error matrix that we actually collected with real numbers by running everything exhaustively, and we say, is it low rank? Is it well approximated by a low rank matrix? Is PCA going to work? Okay? And the answer is like decently, okay? So if you plot the singular values of that matrix, right? So it's telling you how well is the matrix approximated by just a rank 1 model, a rank 2 model, rank 1 model, a rank 2 model, a rank 3 model, a rank 4 model, et cetera, et cetera, et cetera. Well, you can see it goes down very quickly at the beginning. There's still plenty of energy in it as you keep going on. It's like a 200-dimensional matrix, and we've stopped plotting after 50. Okay? So, but by the time you get to like even 10, you've gotten a fair amount of the energy of the matrix, right? Notice this is a log scale axis. Okay? So pretty well, right? Maybe not super accurate, but pretty well. Good. So you see the model improves with higher rank, but also, right, the number of experiments you need to do on your new data set increases with the rank, right? Because if you want to find, okay, here's another quiz, Machine Learning 101. If you want to estimate k parameters, how many pieces of data do you need? Right? How many models do we need to run on our data set if we want to estimate a k-dimensional feature for our data set? At least k, yes, exactly. Great, thank you. Okay, so our approach is just increase the rank until you run out of time. Okay. Now, yeah, the fact that this looks this shape, this should not be a surprise. Basically, every data matrix has a spectrum that looks kind of like this. Okay, you get fast decay at the beginning, you get slow decay at the end. So this idea that you can kind of approximate it with a moderately low rank matrix, this is very general. You should expect it to happen for any data matrix, okay? And we actually have theory for this. Okay, so how do we choose which models to run on our data set? Okay. We want to find this unknown vector, right? So this is kind of classic, anyway, this is classic control theory stuff. Okay, so we want to find this unknown vector. We're going to pick a set of measurements, linear measurements yj, right? So these are the representations, right? These are the model metafeatures, which we already have estimated using our training set, right? And we want to find the x, which is the xm+1. That's the representation of our test data set. Okay. So we're going to pick some models to run on our data set, and here's my model is that I'm going to measure the error of those models on the data set plus some Gaussian noise. Why Gaussian noise? Is that a good model? No, but I can do theory on it. Great. I'm going to estimate x using least squares, right? As we discussed, right? Linear regression. Okay, so here's the formula for linear regression, right? Using my subset of model metafeatures, which I'm calling capital Y here. Okay, stare at this formula, okay, and you do some math. Okay, we haven't done math in this conference so far. This is novel, okay? It's early, but we're gonna do math, okay? It's easy math, I promise, okay? What's the expectation of x hat is x. Good, that's what we want. Linear regression is unbiased. What's the variance of our estimator? Okay, the variance of our estimator is a little bit harder, okay? But here's what it is. It's YY transpose inverse, or equivalently, look at this. You take the model metafeatures, transpose with themselves, so you take the outer product to make a little matrix. You sum them up over all the models, okay? You take the inverse of that, that's the variance. Okay. Do we want our estimator for our new data set metafeatures to have high or low variance? We want to recover the true data set metafeatures. Do we want our estimator to have high or low variance? Low, yes, we want it low. Okay, so does that tell us, what does that tell us about which models we want to choose? We want to choose models whose metafeatures kind of pointing in different directions, right? If they were all kind of pointing in the same direction, we wouldn't learn enough about the vector, right? We would learn how big the vector is in this direction, but we would not learn how big the vector is in that direction, okay? But if we take some models that have metafeatures that are pointing, to span the space, then we learn everything there is to know about our data set metafeatures. Then we're in good shape. Okay, so that's the moral of that story, right? I mean, it's kind of cool, right? So maybe, then you end up estimating from data that, running, several different random forests doesn't give you as much information as running one random forest and one linear regression and one k nearest neighbors, et cetera, okay? That's the moral. Okay, so we have a criterion that we're going to use to choose which models to run on our data set, right? You could also do this with, right, these don't just have to be machine learning models. These could also be metafeatures, right? And we could be choosing which metafeatures to bother calculating on our data set, okay? Okay, so here's what we're going to do. We're going to estimate t hat, that's how long is it going to take you to run model J on your data set, okay? And we're going to have this decision variable, Vj, okay, which I'm going to represent as 0, 1, that says, did I run model J on my data set? 1, yes, 0, no. Okay? So the total time that it takes me to do my, to estimate my x vector is just the sum of the vj's times the t hat j's. Okay, that's how long it takes me to do my meta learning. And what do I want to do? I want to minimize the variance of my estimator subject to that. Okay, variance, that's a matrix. I don't know how to minimize a matrix. That doesn't even make sense. So I scalarized it, and I scalarized it with log det for historical reasons. Okay, great. So unfortunately, that's an integer semi-definite program. Anyone? Okay. If you guys came from constrained optimization, you would know that's really bad. It's really bad. Okay, but there are things we can do. In our first paper, we relaxed it to a semi-definite program. We solved that. That's still not great. In a later paper, we just used a greedy algorithm to choose models one after the other, which can actually prove guarantees good performance. Okay. In practice, works basically equally well. Okay, so now we've done it. Last ingredient, how do we estimate the run times of these algorithms? Okay, so again, it's just another machine learning problem. It's just another meta machine learning problem. So this actually I thought was really cool. We were a little bit worried about estimating run times. Okay, but look at this. So we exhaustively ran all of these methods, right, on all these, OpenML data sets. And then we plotted, then we just estimated how long it would take them to run from this data set using polynomial regression on the number of data points and number of features, okay? This is super, right, it's immediate to evaluate, right? Why polynomial regression? I mean, it kind of comes from theory, right? Most theory would predict that things depend on things like the number of data sets, number of features, and not a very high order polynomial. Okay, so when you plot the actual runtime against the predicted runtime, actually works really well, like within a factor of 2. So these black lines show when you're correct within a factor of 2, and you can see that most of these colors are inside the black lines. Okay, and we don't need a very accurate model, right? We're just using this to make sure we don't run any super slow algorithms. Interestingly, so as someone who comes from the convex side and loves linear regression, I thought it was kind of cool that actually most of the ones that where you're not able to predict well are actually based on linear models. So they're like the SVMs and linear and logistic regression. Okay. I hate to do this to you, but here's another quiz. Why are those ones harder to predict the runtime compared to like tree-based models? Okay, I'm not going to make you answer this one. They depend on the condition number. You guys remember? Who knows about the condition number? I'm actually genuinely curious. Yeah, like a lot of my research is about the condition number. You guys don't know about the condition number. Wow, okay. No, this is really fundamental. I actually think you need to know this even though you're doing automated machine learning now. Okay? So if you're doing linear regression and a bunch of your columns are pointed in the same direction, that's a harder problem to solve than if all of your columns are pointed in different directions. Okay? And if a lot of your columns are pointed in kind of the same direction, that's called an ill-conditioned matrix. Okay? What happens is that one singular value gets to be super large while the others are small. And it makes it really hard to figure out like what should the coefficient be in the small directions because your numerics are kind of swamped by what's going on in the big direction, right? In the direction that everything is pointing. Okay? So, does it matter? Does it not matter? It matters if you think you need to resolve what's going on in the small direction, right? If you only need to resolve what's going on in the big direction, then whatever. Right? But if you also need to actually figure out what's going on in the small direction, you're in trouble. Okay, so that's what's going on here. I'm only pointing this out because it turns out you can speed up a lot of optimization by really thinking about the condition number and fixing the condition number using low-rank methods kind of like what I'm telling you about here. That's not what I'm telling you about, but I've given so many talks on that you'll find them on YouTube if you're curious. Great. Okay, so now we've put it together. Let's put it into a machine learning system. Does it work? Okay. And this, I'm almost like the does it work slides I'm not as interested in anymore because it's old, right? Now, I don't know, use AutoGluon, okay? But at the time, we looked at this and we were like, oh, this is kind of interesting, right? Compared to AutoSKLearn, OBO is doing much better at short times, right? Because we're not computing the meta features, whereas AutoSKLearn always took the time to compute the meta features, which took about 16 seconds, okay? And then after 16 seconds, they're kind of neck and neck. Okay? But this is kind of interesting, right? You get to choose your budget of how long do you want to spend doing your meta learning. And I think that's what's interesting about these low-rank systems. Great. Okay, we're going to elaborate this a little bit. I'm going to show you how to use it for other applications. And then I want to go into some other kinds of methods. Any questions on basic OGO? I was going slow there because it's more useful to understand than to know more things. Yeah?
How can you estimate the runtime without the hyperparameters?
I was estimating runtime using polynomial regression on number of features and number of data points, which I definitely know about my new data set at runtime.
But for most of them, it highly depends on the hyperparameters.
Yeah, so this is what's shocking. No, this is what's actually really shocking about this plot, is you're saying like it highly depends on hyperparameters. And actually when we ran it on, right, and this is, we've gridded out over a bunch of hyperparameters on log grids, and it still is falling within this range. Okay, so what I'm telling you is that for, you know, the ones where you're doing the worst, right, are for these like linear models where it does depend more on the hyperparameters, and we didn't find that it depended that much on the hyperparameters. You could do better by looking at the hyperparameters, absolutely. Yeah, but weirdly, it wasn't such a problem.
Yes, so similar there.
Yes.
If you have like, did you have for random forest, for example, the number of trees? If you have 100 times more trees, it must be 100 times more expensive.
You know, this is this is really an obvious thing that should matter. I'm now wondering if we put in the number of trees for random, because otherwise, how could you possibly? This is a long time ago, so I'm sorry I can't answer that question. But yes, you should put in the number of trees if you wanted to do this. But it's not too hard to estimate runtime. Yeah.
All right, maybe an idea why it is the case for this plot here. What kind of data sets did you use to estimate the runtime?
Yeah. So these were the same 215 mid-sized OpenML data sets. So we didn't take ones that were giant, and that might be part of it.
Yeah. So in our runtime estimation paper, we actually created artificial data sets with a certain number of data points because coverage in higher dimensions is most of the time not so much.
Good.
And then you basically only have a few outliers for larger data sets which are not falling into this realm. And
yeah, that's awesome.
this could explain this effect here.
Yeah,
maybe.
That's awesome. That's awesome. Yeah, as I said, you know, I really want to present to you the techniques rather than to present to you. I'm not telling you use OBO, right? OBO is old at this point. Okay, so but here are the techniques, right? And you can use it with better models to estimate runtime. Right? You can use it with better error metrics. You can use it with other design decisions. Right? It's a sort of general purpose alternative, right, black box optimization method when you have a budget on how many evaluations and when different evaluations cost different amounts of resource. More questions? Okay. Okay, we can elaborate this, we can go even further, okay? So, we started with this problem of choosing the pipeline, right? Choosing the best pipeline, not just choosing the best estimator, okay? So how do we think about this, right? We've got a lot of different decisions to make, and of course we could flatten them all out into a matrix, but then our matrix would not be very square, and this low-rank property holds more for squarish matrices. We'd also be losing a lot of the structure, that maybe there's sort of correlations in which decisions make sense, okay? So instead, let's think about our data like this, okay? So for every data set, for every estimator, for every preprocessor, I'm showing 3 dimensions, but this tensor could have many more dimensions. I'm going to collect the information about the error of the pipeline consisting of, say, that estimator and that preprocessor on that data set in the corresponding entry of this tensor, okay? Now that I've gotten higher dimensional, I probably should not collect all the entries, so I'm going to have to use tensor completion in order to estimate a sort of a compression of this tensor into some tensor format, okay? So here's where, again, like this math of tensor decompositions gets really complicated, and I'm not going to introduce you to it all. There's a lot to do. But there are many tensor decompositions, and often compression works extremely well. So you can take a giant tensor, and you can compress it by 1,000-fold easily, Okay, so the number of parameters on the right-hand side can be much less than the number of parameters on the left-hand side. Okay, and in particular, let's look at the structure for what we're interested in, right? We're interested in what's going to happen when a new data set comes in. You think of that as a new slice of this tensor, okay? To estimate a new slice of this tensor from this model, all you need to do is estimate a new row for this U1 matrix, right? That's what corresponds to a new data set. So again, I only need to estimate R1 numbers, okay? And it's actually even cooler in the tensor model because I get to control R1, the data set rank, independently of R2 and R3, which are like the preprocessor and estimator rank. Okay, so I really get a lot of flexibility here to do compression and also have a low-dimensional thing that I need to recover. Okay. So I get sort of embeddings for data sets, for preprocessors, for estimators, and I could go on and on if I've got more different kinds of hyperparameters. Okay. Okay, I can also sort of vec all this out according to some weird tensor algebra in order to get embeddings of the entire pipeline. Okay, so how do I generalize OBO to the setting, right? Well, in meta-training, I'm going to predict the missing pipeline performance by tensor completion in order to estimate this factored model on the right. And in meta-test, I'm going to run just R1 pipelines, and I get to control R1 to estimate the embedding of a new data set. Okay, so again, you know, worked well, blah, blah, blah. I'm not going to focus on that. Okay, let's move on to problems that I think are more relevant. Okay, Pareto estimation. Okay, so in a lot of modern problems, actually, you kind of know which direction to take your hyperparameters. You know that more is better in a lot of modern problems, okay? So in deep learning, like, you know, you want more training time, you want larger data set sizes, you want bigger architectures, you want more GPU memory. Okay, problem, your budget is limited, right? You can't do all these things at the same time. You have to choose. How are you going to spend your budget? Okay. We used a method similar to OBO in order to choose the best precision for example, right, so say you have a limited memory on your GPU, and you're going to train your deep neural net using low precision parameters of your neural net, activations of your neural net, and gradients, et cetera, right, in your optimizer. Okay, so how do you choose how many bits to allocate to the floating point representation of each of those? Okay? Or how do you design your chip hardware in order to best support deep learning pipelines? Right? How do you trade off among these things? Okay? So that's the kind of question that you can answer using this method. Okay, so let's remember floating point format. How are we allocating these bits? Okay, so we're going to represent numbers as a sign, an exponent, and a mantissa, right? To create a floating point representation for a number, right? So this is IEEE format. And we get to choose how many bits in the exponent, how many bits in the mantissa. Okay. The best precision depends on your budget, of course, right? Of course it does. Okay. So we tried different combinations of these different things in these different parts of your deep learning pipeline optimizer. And as a function, right, so we plotted how much memory they require and what test error they give you, okay? So obviously higher memories perform better in general, right? But at a given memory budget, there is a best architecture, right? A best trade-off, okay? So we can divide these into saying, like, the blue circles, those are the ones that you might use, right? And depending on your memory budget, you're just going to pick the one that has, you know, that meets your memory budget but has the best test error, right? The green ones you should never use. Never, never, never. Okay? How do we figure out which ones are green, which ones are blue? Right? Given a memory budget, right, how do we figure out the best combination of precisions? Okay. Well, the best precision, unfortunately, also depends on your data set. Okay, so we're in the same setting, right? We need to choose among these discrete options. Okay? When you need to choose among discrete options, you could use any black box optimizer, you could use Bayesian optimization. We're going to try these tensor methods. Okay? So here's our setup. So at train time, right, we're going to take a bunch of training data sets. We're going to compute the error that you, right, so we're going to, you know, train our machine learning model, train our deep learning model, and compute the error of that model on that data set after we run it, maybe a fixed amount of time. Okay? We're going to write that down in some error matrix, okay, and then we'll use matrix factorization to find these low-dimensional embeddings for each configuration and for each data set. I'm going to focus on the configurations. Okay. Now, test time. New data set comes in, and you have to decide what precisions to use for the different components, right? Maybe you have to decide, maybe you've developed different GPUs targeting these different configurations, which are known to be non-dominated, and you want to figure out which one to use for your new data set, right? Which kind of GPU to use for your new data set, okay? So here's what you do. You select a couple of configurations to evaluate. Again, you probably want to pick configurations whose meta features span the space rather than all pointing in the same direction, okay? And especially you want to pick ones that are really fast to run, okay? So maybe these are tiny little toy configurations with super low precision that you can run really fast. You're going to use those to decide which high precision configuration you're going to use when you really care about how well your model works, okay? So you're going to evaluate these, you're going to look at the configuration errors, and you're going to estimate the configuration memory of each of these architectures. Now you're going to use linear regression, predict the error that you get using any configuration, and you'll choose the configuration that you think is going to give you the best error for your memory budget. Okay. So again, we say, how well does this work? And the answer is actually pretty good, okay? So the orange ones are the ones that we select as being informative. We're going to those are the ones we're going to bother running, okay? And you see most of them are actually substantially lower memory than what we're targeting. And we're going to estimate which configurations are dominated or non-dominated. Okay, so the pluses are ones that we think we should never use, okay, because there's always some configuration that's better. And the red X's are ones that we think are non-dominated. Those are sometimes worth using. Okay, we're going to look to the right and find the non-dominated configuration that's closest to our memory budget. That's the one we're going to pick. Okay. Now, interestingly, it's not actually non-dominated, right? It's really dominated by this little one, but it's not very dominated. Okay, it's pretty good, and that's what you should expect from these approximate methods. Okay. You increased the rank. You could get one, you could get more sure that it was non-dominated, but it would also take longer to run these things. Okay. Okay. We have 12 minutes. Yeah, let's sort of zoom. Let's go on to large language models for AutoML. Okay. So you think about what are fast ways to estimate models for AutoML, right? What I'm showing you is not what a human would do. The first thing a human would do is they would read the description of the data set, right? You would look at what is the data set about. And if it's a genomics data set, you would do something different than if it's a tabular, data set with, all real values, and you would do something different if, depending on the domain, you would probably do something different. Okay, so here I'm showing a description of a dermatology data set. I'm sorry, it's too small to read. Okay. So it's really natural to ask, can you use natural language processing for this? Okay, so we had a really, I feel like early in the history of NLP attempt at doing this. So we had said, we're going to take the data set and we're going to look at the description and the data. We're going to embed both of them using, compute meta features for both using language model embeddings for the description and embedding the data using the meta features that you saw before. Okay. We're going to fuse these, and then I don't want you to focus on the rest of this, but imagine we're just using nearest neighbors to figure out for our new data set which old data sets it's similar to, and then using algorithms and hyperparameters that worked well on the old data set. Okay. So what's cool about this is, right, the time that it takes you to figure out what's going on is just the time it takes you to compute your meta features for your data and your description, or even just your description, okay, which is super fast. So that means that you can, for example, choose a machine learning model within like 3 seconds because you're not running any models on the data set. Okay. Now, when we did this back in like 2020, the results were not super impressive. Okay. The language models were not very good. The results were not super impressive. In particular, so oftentimes we actually, often enough, we found that our method that was just using these data set descriptions and embeddings, only taking 3 seconds to choose a model, was performing as well as the best automated machine learning methods. Maybe, how often, like a third of the time. It's better than nothing, but, not great. In particular, it's not great compared to a strong single classifier method. Okay? Okay, so this points in two directions. One is, can we do better things with language models, which obviously has become possible in the last year, right? But the other direction it points you to is, wow, you know, random forests, and especially boosted random forests, they're pretty good models, right? Maybe if we don't have a lot of time, why don't we just use those? Okay, so I'm going to talk a little bit about each of those directions. Okay, so large language models. Now, of course, here's what we would do, right? You plug in your data set description to ChatGPT and you say, well, what model should I use, right? And it says, well, you know, you've described this data set. Look, ChatGPT is computing the data set meta features, yeah? And then it proceeds with the following steps: data preprocessing, feature selection, model selection. On the other hand, right, you have to be very careful here with training testing, because the dermatology data set description and many analyses of the dermatology data set already exist online. They existed online before ChatGPT was trained, right? So you can't trust that the results of these large language models on any data set that appeared online before, what, March 2021, are actually valid out of sample results, okay? So you can't trust that doing AutoML like this, you're getting actually valid estimates of how well this AutoML method is performing, okay? Nevertheless, you can see, right, it's a sort of reasonable AutoML method to try, right? We do believe that ChatGPT and these LLMs generalize, yeah? Okay, so how do we generalize? It's pretty obvious once you start trying this. I'm sure many of you have tried this, right? That the prompt that you put is important. And now there are many approaches that do prompt optimization for AutoML and related problems, right? That are sort of easy to generalize to this. So I'm just highlighting a couple of them. There's in-context learning approach that Chen talked about and Richard Song in their tutorial. For example, you feed the LLM examples of, you know, here's the task and here's the best pipeline. You give it a bunch of examples like this and you say, here's the new task. You wait for it to tell you a new pipeline. Now, is it good, is it bad? You know, how much performance can we extract out of it? These questions are not known, but I think they're exciting directions, right? Okay, Optformer, Evo prompting, and LLMs as optimizers. Okay, I had, you know, I'm not going to tell you too much about these because you can look them up. I think these are really interesting approaches, and I think you'll like reading about them. But I think one point is that decoding is still hard. Sometimes you don't even get outputs that are properly formatted. You need to figure out how to get the LLM to give you the kind of answer that you want. And Richard made this point pretty strongly. Okay, this is also my student Chungren Yang, but work that's not with me that he did at Google Brain. So I think this is really cool, right? You say I've got some texts with their corresponding scores, right? You say, like, say that I'm going to be using this as the prompt. Let's figure it out. That gets 61. Say I'm going to be using let's solve the problem. That gets score 63. I give more of these, right? And you say this is how you're going to apply your text, right? You're going to insert this prompt, right? That sort of helps improve the answer right at the end, right? And you say, you know, this is the output you get, right? And you say write new text. So write new text for this, right? And so you're using, I think this is a really clever system for using the LLMs to design better prompts for LLMs. Okay. So you can use this for whatever LLM task you want. Right? You can get it to, for example, AutoML using this. Okay. Great. I'm not going to say any more. Okay. It's a big direction. You know, we don't know how successful it's going to be, but I think, you know, we're going to have to base a lot of the AutoML work that we do on these, because once we build on things that are greater, we can go farther. Okay, let's try a completely different direction in the last 5 minutes of the talk. Okay, so I showed you that there's no free lunch. There's theorems that say there's no free lunch, but what about just a cheap lunch? Okay, what about a cheap lunch? How well can we do, you know, I mean, this is maybe what people do in practice anyway, right? If you don't have a lot of time, what model are you going to use? You're probably just going to use like a random forest or XGBoost, right? Maybe you want some feature selection on top of that. Maybe you want some interpretability on top of that, right? If you're not actually going after the highest prediction accuracy, oftentimes what you're going after is interpretability. Okay. If you've got really high budget, then do neural architecture search using LLMs and evolutionary prompting and blah, 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 you know. Train it on 10,000 CPU cores for 5 days, right? Great. Okay. But these models have hyperparameters. And a lot of the direction of my research recently is trying to figure out, instead of choosing the best algorithm, the best hyperparameter, why don't I fix my algorithm and try to get rid of the hyperparameters, right? Hyperparameter search can take a long time, right? I don't have to tell that to this audience. And if I can design algorithms that don't have hyperparameters, right, or have very easy to choose hyperparameters where more is better, I can do much better, and I can deliver good models much faster. Okay. So in trees, what are the main hyperparameters? It's the number of trees, okay, which I'm writing as the number of bags, bootstrap samples of your data set, and the number of boosting iterations. Deep learning, it's the batch size and the learning rate, okay? So I have work on getting rid of the learning rate using stochastic quasi-Newton methods. I'm not going to talk about that. I do want to talk a little bit about building interpretable tree-based models where it's very easy to choose the number of bags and the number of boosting iterations. Okay, so that's work that I call control burn, and I'm going to use the last 5 minutes to talk about it. Any questions about, I don't know, set up motivation first? I think this is the big question that I really want you to think about, is when is it worth doing AutoML to choose the best model? When is maximizing predictive performance the thing that you care the most about? And when is it something more like a good enough model that you can understand and use to design your next decisions, okay, in an applied domain? Okay. So here's the sort of control burn in 5 minutes, okay? So we're looking for interpretable tree-based models, okay? Decision trees, they're pretty easy to explain. They're not very accurate, and they're not very interpretable. So for example, here's the visualization of a decision tree. You can see if you make a decision here and here and here and here and here, right? I mean, you can't explain that to anyone. You can't like tell your doctor, right, this is how I am telling you the risk factors for your patient. Like, no, you can't explain that to a patient and say, oh yeah, I believe that your risk for liver disease is really high because of this. Impossible, right? No one can understand that. Okay. Random forest, more accurate, too complex. Some of the trees is too hard to understand. Boosting, even more accurate, even more complex. Explainable boosting machines. This is a methods that were developed by Rich Caruana, Johannes Gerke, and many other people that I really was inspired by. They're really cool, okay? So if you don't remember anything else from this part of the talk, it's explainable boosting machines are really, really cool, okay? And here's what they construct. So they build a bunch of trees, but the thing is they're building a forest using boosting, but everything that they're constructing, every subtree is just a stump. It only uses a single feature. Okay? And because it only uses a single feature, I can add up the contributions of all the trees that use the same feature, and I can plot them. Okay? And they make these plots that they call shape functions, and they also they take a long time to fit them so that they can actually get confidence intervals on their shape functions. Okay? And they say, look, as a function of, for example, this is in a medical application, the BUN level of some blood test. Okay? So as a function of the BUN level, here's your risk of pneumonia. Okay? And they can say things like, this is so cool. Okay? They can say, as your BUN level goes up, your risk of pneumonia goes up, 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 and then it goes up, 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 it gets really, really bad until you get to BUN level 100, and then your risk goes down. Why does your risk go down when you get to level 100? That seems like a very round number. And Rich Caruana goes and he talks to the doctors, and they say, oh yeah, we treat really aggressively when the BUN level is above 100, because we know the patient's really in trouble. Okay? So you can discover, this is the use of explainability. You can discover these treatment effects. It's not the case that patients with BUN levels above 100 are in less danger, okay? This is a treatment effect. And maybe you actually want to edit that out of your model and wipe out that treatment effect so that you can actually accurately estimate the risk before treatment. Okay, control burn tries to do something similar, but we're trying to work in the context of very high-dimensional feature spaces and where you might want to include interactions, okay? In a setting, you don't want to estimate shape functions for every feature. You want to subset the number of features that you're going to use, right? To make it really interpretable, you want to be able to select what are the 3 or 4 or 5 most important features, okay? And maybe if there are interactions that are important, which interactions are important. Okay? So to be able to do that, we're going to need some kind of sparsity enforcing penalty. And so here's the picture. This is why I call it control burn. We're going to build giant forests with lots and lots and lots and lots and lots of trees, and then we're going to burn down most of it. Okay, I come from California. In California, okay, no, this is what you do, right? This is what you do. If you don't burn down, so you want a controlled burn that just burns the things that aren't important, like the undergrowth, and leaves the really big trees. Okay, that's a good way of burning your forest, and you're left with a sparse forest. Okay, that uses a small number of trees. That's what we want. Great. Okay, so I think this is the last slide I'm going to show you. So this is as long as you need to give me your attention. Okay, so here's the algorithm. You build a forest, okay, a large forest. You keep only the features that are needed for the most important trees using something like lasso or best subset selection. At the end, you could refit another model, maybe an EBM model, on the most important features. Okay, so if you're doing this, you need trees that are the right shape. You need trees that are simple enough, right? If all the trees in your forest, if you built them all using, you know, depth 5 trees that you got using, I don't know, your boosting algorithm, right? Then any tree has sort of complex interactions. That's not what you want. What you want is to somehow make sure that you've got trees that capture the main effects, and then move on to trees that have interaction effects like this, and then move on to trees that have higher order interactions, okay? And that's going to ensure that there exists a subset of the forest that has just a small number of features and a small number of interactions that still uses the, that still captures the information in your data set, okay? Okay, so we've got a method for doing this that boosts and bags. We call it bag boosting. We have a method called double bag boosting. These are ridiculous names, but they actually work. Okay, so if you use these, you can get performance that matches the performance of a sort of baseline random forest full model using only like 6 or 8 features. And compared to using random forest feature importance, you actually do much better on a substantial fraction of data sets. Interestingly, sometimes the sparse model performs better than the full model. Like, for example, the full model here is really bad. The sparse model here is really good. Okay. If you want to see how to interpret this, here's a demo. That's all I'm going to say about it. Okay, so big picture, what's going on? Automated machine learning is a machine learning task, right? So you can apply, you know, most machine learning methods to automated machine learning. I think we've seen that here, that right in it's what I find fun about this conference and this community, right, is that the full gamut of machine learning techniques is also used for automated machine learning. We're all sort of present here, okay? So you have to ask yourself these questions. What's the data? Is it just numbers, or is it also the description and the header, right? What is the training set? Is it just the present training? Is it just the present data set? Or can I look at other data sets that are similar? Is active learning allowed? And frequently it is, okay, in real applications. Okay, so maybe you're allowed to train on other data sets, maybe you're allowed to train simpler models first, maybe you're allowed to ask experts what they think about your answers in a, you know, you think that things unsupervised, but actually maybe you do have access to a little bit of expert feedback. What's the target speed of inference? You're going to use really different models depending on how much time you have, and there are a lot of applications with, you know, in like scientific domains where the users don't have a lot of patience and they do want answers fast. Okay, and they want answers that they can understand and interpret, okay, and use to make decisions. Okay. Prognosis for AUTOML. I think this is a question that really interests me, and where I don't know what the answer. I'm really excited to see what the next couple of years bring. Are we going to arrive at one model that's just so much better than everything else because it was trained using, you know, the US GDP of resources? Right? That it's not worth using any other models to do anything, who knows, right? So will a sufficiently complex transformer turn out to be the best model, enough better than everything else that actually we don't need to do algorithm and hyperparameter search? Will an LLM with good prompts turn out to be such a model, right? That you don't need to use anything else? Should we be optimizing hyperparameters, or should we be focused on eliminating them, designing better algorithms that are essentially hyperparameter free? So I think these are big questions. I'm really excited to see what happens in the next several years, and I'd love, if you have any questions on what I've talked about or sort of ideas about the future, I'd love to chat. Thank you.
Thank you so much. Take a couple of questions.
Yes.
Yeah, thank you very much. Excellent talk. I was wondering a little bit of a technical question that I've been wondering since I started my PhD, and I'm still not sure whether I have a really good answer to that. When you do, for example, this matrix factorization, what do you think is the best loss function to take here, right? I mean, Nicolo Fusi did like this probabilistic approach, but then there's also ranking approaches or regression approaches, and all of them have their pros and cons.
Yeah, so this really, so okay, my PhD thesis was largely on different loss functions for matrix factorization, and I was really into the different loss functions for matrix factorization. And again, this is, I'm telling you about the arc of my research, now I'm like, just use quadratics. It's weird, but actually just using quadratics works really well. I first observed this in this OBO project where I told Chandran, I was like, oh yeah, you need a ranking loss. And no, the quadratics work just as well from the perspective of designing an AutoML system, okay? That's really weird, and it bothered me for a while, and then I wrote this paper with Alex Townsend called Why Are So Many Data Matrices Approximately Low Rank? So we actually have theory for why, the theory is in the infinity norm. Like, this matrix should look approximately low rank. So in the infinity, that means the difference between a low rank matrix and your matrix, the absolute value of any entry's difference is bounded, okay? And you can actually prove that as the data matrix gets larger and larger, it's better and better approximated by a lower and lower relative rank matrix. Okay, so now I just accept it doesn't even matter what your metric is. You could use L infinity, and you'd get a good low rank approximation. Okay, now I don't know how to compute that. L2 I know how to compute. It's so much easier to compute than anything else that you might as well just use L2.
All right, thank you very much.
Yeah, thank you for this great talk. I wanted to ask a bit more about the last bullet point, whether optimizing hyperparameters or eliminating them. Carola Dörr was arguing recently in a paper about tunability of algorithms, which, according to her, is a great thing. So if you have many hyperparameters, you are much more flexible to adapt to everything, right? And if you have very strong hyperparameter optimizers or tuners, then of course we don't eliminate them because we are good in figuring out what is a good setting anyway, right? And on the other hand, what I've also observed is that some people trying to eliminate them by, hand design heuristics internally, so hiding them somehow. We're also a bit skeptical about is that the right thing to do. So what's your take on that?
I mean, it's not clear which of these views will win. I think it really depends on, if you imagine that if your ultimate interface to the biggest, giantest model that was ever trained is a ChatGPT-like interface, right? Then you don't have hyperparameters anymore. So I don't know, are we going to live in that world or are we going to live in a different world? I realized I didn't actually have time to tell you about how we eliminate hyperparameters in control burn. But basically, the number of bags, the number of trees, you just want more and more and more. The fit gets better and you don't overfit. And the number of boosting iterations, because you've got bagging and boosting, for any sample, you have a bunch of trees that were fit out of sample, and you can evaluate the performance and tell whether a given boosting iteration helps or hurts. And if it hurts, then you stop. Okay, so in control burn, we really don't have hyperparameters other than the sparsity, which it's appropriate for the user to control. Okay, so this is an example of what I mean by eliminating hyperparameters, and I feel that we're not losing performance by eliminating those hyperparameters. Okay, one is just a budget constraint, and the other we can actually say when you should stop. Okay. So I don't know. We'll have to see. We'll have to see whether one model really takes over, or whether we always have this complexity and need to adapt. But in general, I prefer algorithms without hyperparameters because even, with all of the incredible innovations going on in the AutoML community, it's still a pain to optimize hyperparameters, especially for yeah, I just, it makes the code more weighty. It makes the process just a little bit more complicated. And you can say, yes, we can do AutoML in one line, but just like, you're losing interpretability, you're losing visibility. The scientists are a little more nervous about it. Like, there are things to like about not having hyperparameters. If we can do it, yeah.
Thanks for the great talk. Direct follow-up on
Yes.
hyperparameters. So we have this approach, TAP-PFN, that doesn't actually have any hyperparameters. And what I've seen some people on Kaggle say, oh, it seems like an interesting approach, but I don't like it. I can't tune its hyperparameters. There's no hyperparameters to tune. So what do you think about that? And I talked to Dev Rishi, who evangelized AutoML for Kaggle, and he said, in the beginning, people use it a lot, and then sort of there was churn. People didn't use it because they felt it's a dead end. They can't do anything with it. It's just automated, and they don't iterate on it. So, yeah.
Yeah, no, it's interesting. People like to have jobs, right? And it's hard to know, like, there's like creative destruction, right? And new technologies do destroy jobs. And the people who spent their comfortable careers, tuning hyperparameters by hand are uncomfortable when you give them algorithms without hyperparameters and they don't know what to do with their new leisure time. So I think we all need to develop, more exciting hobbies. Yeah, I'm not sure. It's exciting to see what the future will bring. Yeah.
All right. With that, let's thank the speaker again.